We were talking about lateral control prior to lunchtime. Now we're going to look at directional control, primarily by the rudder. Essentially, you've got two directional control requirements, one for single engine airplanes and a different one, so to speak, for multi-engine airplanes. And of course, it's essentially a function of the rudder. And the reg allows a rudder force of up to 150 pounds. Now that's a lot of rudder force too, okay, 150 pounds. Some of you may do leg push-ups or that sort of thing. The gym, pretty good force that's allowed and covered in FAR 23.123. And then 23.233 talks about directional stability and control, and about a 90-degree crosswind. The airplane has to be able to handle a 90-degree crosswind that's at least 0.2 times the stalling speed flaps down. And then there's some other requirements there as far as crosswind. Those are primarily for single engine airplanes. For multi-engine airplanes, we have some other requirements. Here's one, be able to make heading changes on a single engine with a critical engine and operative. And of course, then you have to be able to have a VMC, or minimum control speed, with one engine failed. You have to be able to control the airplane down to a speed of at least 1.2 times the stalling speed in the configuration. For small airplanes, large airplanes, transport airplanes, they have several different minimum control speeds that you have to be able to meet. So essentially two requirements. Here's a minimum control speed. And notice that for this has to be done with rudder. And for airplanes, this is primarily for commuter airplanes. Also having minimum control speed on the ground, and if you fail an engine at the minimum control speed on the ground, VMCG as it's called, you can't deviate from, say, the runway center line more than 30 feet. You deviate more with an engine failure, why you don't pass. So you have to have an adequate rudder to be able to do that, in addition to the being able to maintain the in-flight minimum control speed. What you are allowed to do, if you'll notice right there, you're allowed to have an angle of bank into the good engine of 5 degrees. Now, if you've taken a multi-engine rating, a lot of instructors don't do that. They want you to keep wings level. But it's a lot harder, and then speed is higher if you don't bank into the good engine. So it's a good idea to bank into the good engine should you have a failure. Okay. Things that set the directional control requirement for single engine airplanes. Rudder required to reduce side slip to 0 in a turn. You know, if you just bank the airplane, you introduce some side slip. For those of you who are pilots, you know that the ball will probably go out one direction or the other, right? If you don't coordinate it with a bit of rudder. You would like to keep that ball in the center because you don't want side slip because, number one, it makes the airplane less efficient, more drag and that sort of thing. So we really don't want side slip in turns or anything else. So one of the requirements for the rudder is to be able to reduce it to 0 in a turn. On takeoff, say if this is our propeller turning, when we put an angle of attack, the downgoing blade produces more thrust than the upgoing blade due to that angle of attack difference. That tends to make the airplane want to turn to the left. Like I say, those of you who are pilots, you have to put in right rudder, right? You have to hold right rudder. So you have to be able to counteract that, and we call that P factor, and it's due to slipstream rotation and that sort of thing. And the fact that the downgoing blade of the propeller produces more thrust than the upgoing blade. Rudder required to maintain a constant heading during crosswind takeoff and landing. Back in the early days of aviation, we didn't actually have runways. We just had big fields. And so you could always take off into the wind. You know, it was just a nice big flat area, and you could take off whichever way the wind was blowing, you took off that way. So you didn't have to worry about it too much. But today, you know, we have runways. And unfortunately, the wind doesn't always blow down the runway. In fact, here it's not uncommon, particularly after frontal passage, for both of the main runways here in Melbourne to be pretty much direct crosswinds. And so we have to be able to counter that crosswind on takeoff and landing. And the last thing, rudder required for spin recovery in single engine airplanes. We're trying to do it, all airplanes currently are required to demonstrate recovery from a one-turn spin. Okay, within one additional turn. Now that rule came about back in the old days when airplanes were very light compared to what they are today. The wing loadings were quite low. And doing a one-turn spin, you didn't lose much altitude, 500 feet maybe. Today, most of current general aviation airplanes, if you do a one-turn spin and recover, will require 800 to 1,200 feet of altitude. Now, how high is the average traffic pattern?
1,000 feet.
1,000 feet. So it doesn't make much sense anymore. And unfortunately, about 96 or 7% of those kinds of accidents occur in the traffic pattern. And so I've always thought it's much better to hit the ground in the spin than it is the 120 knot recovery from the spin. Okay, because the spin is at below stall speed, okay? Airplane's descending. Its forward velocity is, after a while, you know, if you spin from high enough, it becomes vertical. Initially, there is some forward velocity, but the thing of it is, still yet, if you hit the ground in a spin, you're more likely to survive it than you are if you hit the ground on the recovery, which is generally around 120 knots in most of today's airplanes. So the spin recovery thing is, for the one turn spin, is kind of going away. Now, you will see that airplanes, if you go to an air show, you always see somebody in an unlimited aerobatic airplane doing a spin, okay? We know how to design airplanes to recover from spins, but if you do, they all look like unlimited aerobatic airplanes if you design them so they will recover. Those airplanes are nice for air shows, but they're not something you want to take mom and the kids in, okay, or your husband or whoever, okay, for you ladies in the class. So, the spin rule is going to go away. The one-turn spin rule in the current FAR 23, the one that's out for comment right now, there is not going to be a one-turn spin requirement anymore. Okay, that's going to go away. And it's been a long time coming. But anyway, you use the rudder for that. That's the first control in a spin. That's the first control you reverse. And it sets up the side slip necessary for the airplane to auto-rotate. Okay. Well, multi-engine airplanes aren't spun anyway. Now you may ask why. Well, the FAA in its infinite wisdom, okay, said multi-engine airplanes are flown by more qualified pilots. So they aren't as likely to inadvertently get into a spin to begin with. And if they do, multi-engine airplanes aren't likely to recover because of the inertias. Here's an example of a multi-engine airplane. Engine's out here. This one has wingtip fuel tanks. Our fuel in the wings, a lot of inertia along the wings. May not recover anyway. So they said, okay, multi-engine airplanes don't have to spin. However, we have a case where we may lose an engine. And so here we have the yawing moment due to an engine failure. The thrust of the operative engine times the distance out from the center line. So that produces this yawing moment. The right engine has failed. It's out. This one is still operating. So it's going to try to turn the airplane into that dead engine. If we write that in coefficient form, it looks something like this. So the yawing moment coefficient due to the engine failure is the thrust of that engine times the distance out divided by dynamic pressure and wing area and wing span. Now, the other thing that isn't included in this equation is that if this propeller is not, if it's a propeller-driven airplane and the propeller is not feathered, which means turning the propeller so it meets the relative wind on an edge, if it's not feathered, it's trying to run the engine by the propeller and is taking energy out of the air. So you may have another force operating in this way, which makes that yawing moment even worse. So generally, when you have an engine failure, the first thing you do, bank into the good engine, into the one that's operating, put in the required rudder force to keep it from turning, and then you go about feathering the failed engine. And there's a saying that's dead foot, dead engine. Okay, so the rudder that you're pushing on is on the side that the engine is operating. The one that you're not putting any force onto to keep the airplane going straight is the engine that's failed. So then you reach up and you pull the throttle back to idle and see if anything changes. Oh, nothing changed. So it's that engine for sure. We've identified it. Now we reach up and we get the propeller control and we pull it back into feather. And then that drag that we had there goes away, okay? So, and if we're in level flight, we can take that yawing moment coefficient equation, this one here, and we can solve for the QS part, which is weight over the lift coefficient. Then the yawing moment coefficient is equal to the lift coefficient times the thrust of the operative engine times the distance of the operating engine out from the center line divided by the weight times the wingspan. And of course, for propeller-driven airplanes, the thrust of the propeller is essentially 550 times the propeller efficiency times the brake horsepower divided by the true airspeed. And we can make that substitution, and the equation comes out looking like this, where here's the brake horsepower, the lift coefficient, and the distance out, true airspeed, the weight, times the wingspan. Now, if we plot that up for various speeds, or various coefficients versus speed, if we hold the horsepower and the propeller efficiency constant, we can plot that versus true airspeed. And if we oppose that available for a maximum rudder deflection, okay, here's the CM that would be generated by our maximum rudder deflection, and here's the curve of yawing moment coefficient for asymmetric thrust versus airspeed. Then we find the speed for minimum control with one engine feathered. Well, since if an engine fails, a propeller isn't feathered, it creates that negative thrust or drag, then, you know, this is plot that I've drawn here is just give you an idea of what the minimum controlled airspeed is going to be. So when you go out to test to find the real one, you sure wouldn't want to start back here someplace, would you? Okay? You know, you would want to start out here with a speed and work down into that. So, but this is a useful plot in determining, you know, in doing the flight test. Well, a fellow by the name of Wes Bourbon. Wes Bourbon, some of you may have heard of Burt Rutan. Wes Bourbon and Burt Rutan worked together for Jim Beatty. You may have heard of Jim Beatty. He has designed a number of airplanes. He's also kind of a charlatan in that he designed a little airplane that he sold a lot of kits to a lot of people for $500 was the initial down payment. Most of those people never got the rest of the kit. But he had designed this little airplane. In fact, Wes Bourbon, who the fellow I'm talking about, Les said that Jim Beatty was a genius with a short attention span. Was his quote. He said, you know, Jim Beatty really, a little BD-5 It came out in two versions, a propeller-driven one and a jet, okay? And it was all about as long, maybe, it wasn't twice the length of one of these tables. Okay, cute little airplane. Actually, it was a cute little airplane. But they had a lot of engine problems with it in the development. And Les Bourbon had worked up, he knew if the engine failed anywhere in the traffic pattern, he had it figured out. He liked to do energy maneuverability, and he had it figured out where he could manage to get back to the airport and land wherever the engine failed. Well, Les also liked to do a lot of stuff, and part of his thing was that he started looking while he was working for the FAA. He left BD flying the little BD-5, which as they wasn't much longer in one of these tables, and went to work for the FAA out in Seattle as a test pilot on a 747. Okay, now from flying one of the smallest airplanes in the world to flying one of the biggest airplanes in the world. Okay, that was. But anyway, he come up with some of this stuff, and he took these equations for engine out and solved them for a number of different things. You know, you can solve those equations for the rudder required to have 0 side slip with no bank angle, or you can solve it for the bank angle for 0 side slip. You know, if you put in enough bank, you can get 0 side slip. Or the rudder required for 0 bank angle, side slip for 0 bank angle, side slip for 0 rudder deflection. Okay, how much are you going to let the airplane side slip so that you don't have to deflect the rudder? And the bank angle for 0 rudder deflection. Okay. Well, from the engine out minimum control speed is critical where the thrust is the highest. And for a normally aspirated reciprocating engine, like these airplanes out here on the line, multi-engine airplanes, this Piper Seminole, the thrust is the highest at sea level. Well, how are you going to test at sea level? You're not going to want to fail an engine right off the water out here, because you'll probably make a big splash. You know, it'll hit the water before you can do anything. Well, Les showed through his mathematics that VMC increases as weight decreases. Now, if you go back to the rule doesn't say anything about that. And so most airplanes of this category were tested at, everybody just assumed it was gross weight. And what happened was that one airplane in particular that was used for a lot of pilot training prior to the Seminole was the twin Comanche. Because it was an inexpensive little airplane, it was a fast little airplane. Used small engines, so it didn't cost a lot of money to operate, so it was used for multi-engine pilot training. Trouble was they had a lot of accidents, because during that period of time, and may still be, I haven't looked at the multi-engine flight test requirements lately, but at that time you had to demonstrate, I know when I took my multi-engine rating, I had to demonstrate VMC. I had to get to the point where the airplane was starting to roll off. Of course, the way you stop that, if you've got some altitude, you pull the operative throttle back, okay? You know, then you're back under control. You're above VMC because you have an infinite number depending on where the throttle is, okay? How much thrust you're producing. Well, Les Bourbon decided to take a look at the twin Comanche and the accidents. Well, we can see there's a large number of variables, BMC, and I don't know if put this other slide in here or not. No, I need to go back. Anyway, he came up with a plot for the twin Comanche of VMC versus weight. And what he showed was that the VMC at a light weight, where most everybody was flying to do this test and the demonstration for multi-engine pilots, was actually was above the published minimum control speed. And so people were getting bit, and of course, what happens once it went, the airplane didn't have real good stall characteristics because it didn't have any washout or twist in the wings. And, you know, once it departed controlled flight, which was the surprise of both the pilot examiner and the student applicant, once it departed controlled flight, it usually spun and crashed. So, anyway, that was, then the FAA came out with a thing that said, hey, you know, watch out here. You need to make sure that the lightweight VMC is actually, you know, provided rather than the gross weight. So we see there's a large number of variables, and you have to hold some constant and extrapolate others. And essentially the basic tests fail an engine and vary airspeed. When you do that, you record side slip, aileron deflection, and rudder deflection. And since we know the maximum deflection is the control surfaces, we can find VMC for a condition by extrapolating the data. And here we go. Here's side slip. Notice that that's maximum of 2 degrees side slip, which is not too bad. It just looks bad. This is aileron deflection. You can see what's happening with aileron deflection. As we slow down, we're going to start the test up here, and as we slow down, we notice it requires more aileron deflection. This is rudder deflection down here, and of course, in this case, we have about 25 degrees of aileron deflection available here, and we have 15 degrees of rudder deflection in this case. Well, notice that comes out to a VMC of, on this airplane, which was a Cessna 310, of about 78 knots for this condition. Okay. And then we try another altitude, and we do the same thing. 3 different altitudes we've done here. Again, side slip. Notice this one I held that pretty good, not much better than that one. And notice that as we changed altitudes, the VMC tended to decrease until here we had 72 knots. Then we take these data here and we plot them up versus altitude, okay, and then extrapolate it to sea level. That way we don't have to test at sea level. Okay, we're getting around that point. Now, this is a dynamic maneuver as a rule, because the engine fails, you know, it don't say, oh, you know, give you a chance to get all set up. When the engine fails, it fails. And you have to respond. Well, so this gives you what we might call a static VMC. Okay, because we're doing it in a static condition. So once we know this number again and have this curve, we can go back up here someplace and actually do failures until we get down and see if that line is a good line for the dynamic case. And we could do that at a couple of altitudes. And if there is a difference, then we can draw a parallel line and extrapolate it to sea level and get to the actual number. used to do this in my class at UT. Unfortunately, our next acquisition at FIT is a multi-engine airplane. Haven't told Brian. But anyway, you know, this is an interesting test to do, and we can do this. In fact, that data that's in my book was done by, I did the flying, but it was one of my engineering students at UTSI. Fellow now works for Gulfstream in Savannah. His name is Barry McCarthy. And Barry, that's Barry's data that you just looked at. So that's how you would go about doing VMC. Here's Les's curve, Les Bergen's curve that I was looking for a while ago. I got ahead of myself, I guess. But notice that here's FCG, 30% MAC. And notice that at 4,800 pounds, which was the gross weight on this airplane, that showed up at 88 miles an hour. Okay, take that across, it's 88 miles an hour. But if you're at forward CG at lightweight, you're above that speed. Notice that it's about 89 miles an hour at lightweight. Even at forward CG. At aft CG, looky how high it gets. You know, here's the number that got published. And there's what's happened if you let the airplane get light. So if somebody is doing this test and they're gradually slowing the airplane down, expecting to get down to about 88 miles an hour before it starts to depart, and all of a sudden they get to 91 miles an hour and it departs, whoa, surprise. The biggest thing you can have, or one of the worst things you can have in aviation, is a surprise. Okay, you don't want a surprise. You know, you don't want a surprise from the weather or almost any other thing related to flying an airplane. You'd like to know ahead of time. Well, what was happening was these folks were getting surprises because as the weight increased, the minimum control speed went down. In fact, at aft CG, at forward CG, it was actually a little, lightweight. It was actually higher than it was at heavyweight at aft CG. Okay, well, how can we determine, shifting gears here, that's the minimum control speed issue for multi-engine airplanes. Maybe we want to find the derivative C in delta R. We can calculate it using this equation because we can come up with the lift curve slope of the vertical tail, knowing that it's a symmetrical airfoil, probably on the order of 0.009, NACA 0.009 airfoil, which means that it's 9% thick at its max thickness, 9% of the card thick. Or, so we can calculate, we can find that out of the literature. Control surface effectiveness factor, and if you have a copy of aircraft performance stability control by Cortland Perkins and Page, they give a way of determining this in there, or I think that probably came out of an NACA report. If you dug around in old NACA documents, you can get that. And of course, this one, vertical tail effectiveness factor, is just the dynamic pressure at the vertical tail over the free stream dynamic pressure, and generally that's about 0.9. So you can calculate C and delta R. Or you can determine it by flight test. And you already have the data to do that. You got it from loading at 2 different CGs doing lateral directional stability. And we'll show you how that came about. So we measure control positions in a straight, steady side slip at 2 CG positions. That's what we did last flight. And if we assume the bank angle is small in a straight, steady side slip, we can ignore the rudder side force and write the lateral directional equations as lift coefficient times the bank angle with side slip plus Cy beta, okay, the side force due to side slip, and that equals 0. And then we have rolling moment coefficient times, or rolling moment coefficient with side slip plus CL delta A, the rolling moment due to aileron deflection, times the aileron deflection with side slip. That's data you have. And then the directional control coefficient, Cn beta, plus Cn delta A, so directional, the coefficient with aileron deflection, times the change in aileron deflection with side slip, plus Cn delta R times delta R with beta. So how much side slip did you have with beta? Again, you have all of this from the data that we got the other day. And if we shift the CG by some increment, which we did, then the only coefficients that change are Cn beta and Cn delta R. And since the tail length is large in comparison to the change in CG, you know, change CG probably, what, a couple inches? You know, how long is a tail? I mean, it's well over 100 inches, okay? So it's, compared to our CG change, it's large. And we can assume Cn delta R to be independent of the CG position. And that leaves those equations, only Cn beta as a variable. And we find the change in Cn beta due to the CG shift by reference to that in the following equation. Change in Cn beta is side force coefficient times change in CG position over the wingspan. And so here we have a direction. Here's a length from the CG, the first CG, all the way back to the tail. And we move the CG back here. And so we can define that Cn beta 2, which was the Cn beta at this position, is equal to the Cn beta at that position, plus the change in side force times the delta CG, this distance right here. And we can then solve the side force coefficient due to side slip. We can determine that using an equation since neither the bank angle versus side slip nor lift coefficient of the airplane are a function of CG. And so we write an equation for that, and those CG positions, and subtract one from the other. So delta Cn beta plus Cn delta R is delta R over change in rudder deflection versus side slip. So the slope of that line. And then we substitute that into this equation, and we solve for Cn delta R. Lift coefficient we can get since we know what the airplane weight was, And using this equation, we can come up with that. All that's available from the bilateral directional stability flight test at 2 separate CGs. And we know the length of the tail. We can find the side force coefficient due to rudder deflection, Cy delta R, by use of Cn delta R. And so we've got that from this equation. We substitute in here. These are known values, and we can come up with the side force that the rudder, the vertical tail generates. You know, essentially, that's what this is. Vertical tail generates lift in this or this direction, whichever way you deflect the rudder. That's a side force. That will actually tend to move the airplane sideways. In fact, when you make a crosswind landing, that's what you do. You bank the airplane, change the lift vector, and the airplane's going to want to turn, so you deflect the rudder to keep it from turning and generate a side force that helps cancel the drift, okay? I was telling somebody, I don't know if I've told this class, but we had an airplane at UT that had some big surfaces, vertical surfaces on the wing. And you could move those vertical surfaces together and the rudder and generate direct side force. And what was neat about it was you come in a crosswind landing, you lined up with the runway, you see how much you drifted, and you just dialed in the side force necessary to stop the drift. And then you could land wings level. You didn't have to bank the airplane. And it was pretty neat as a way to do that. And when you think about it, on transport airplanes that have very long wings, your crosswind limitation may not be necessarily control power limited. It may be the fact that with that long wing, and particularly if it's got an engine out there below the wing, it may drag the ground. It's not something you want to happen. So that may limit you in crosswinds, where if you had direct side force, you could just land the wings level. Be fairly neat. Okay, another way of doing this, another flight test method, determining Cn delta R, is to mount a little parachute out here on the wing. And of course you know how far out that is, okay? You can determine the drag of this little parachute in a wind tunnel. And with that, you can come up with how much, and knowing the rudder deflection, you can come up with Cn delta R over. So this particular derivative is fairly easy to find in flight test if you want to do it. Okay, questions?